Hello everyone, welcome to the week 6 project which is on deformation and stretch in 3D bodies. So a quick overview of what I'll be discussing in this presentation. So I'll be quickly going through the parameterization of my 3D body, and then I'll compute tangent vectors to the undeformed 3D body, which is given by nothing but the the partial differentiation of the parametric equations. After that, I'll define a deformation map on the 3D body. And once the deformation map is defined, differentiating it will give us partial differentiation of the deformation map will give us the deformation gradient. Then I'll define some 3D curves on my body. And lastly, I'll compute the deformed and the undeformed length using MATLAB. And I'll verify for one curve using hand calculations. So the body I have chosen is the I section, and this is the parametric equations and how we code it on MATLAB. So the tangent vector is given by partial differentiation of the parametric equations. So my body is B1 is this bottom flange, B2 is top flange, and B3 is the web. And the parameterization for these are quite simple, and so is the differentiation, that is the tangent vectors. Now, the defining the deformation map. The deformation map I have chosen is nothing but just the deflection the beam would undergo if a load is acting on this point. Let's say the magnitude of load is P, and let's say this is a cantilever beam. So the deformation it would have under that loading condition is what I have chosen the deformation map. So basically this is a vector field. Adding x plus this and y plus 0 and z plus 0 gives us the deformation map. Taking its differentiation gives us the deformation gradient. Now this is the way higher. Now these are the curves I have defined on my body. There are 12 curves that I have defined for body 1, which is this one. 12 curves for body 2, and only 4 curves for body 3, which is the web. And here is the way how this is the to compute deformed and undeformed length. We have to define the deformation map for each body and the corresponding deformation gradient. And here is the way how I have done in the MATLAB. And from MATLAB, I get the length as these. Note here, since the deformation is only on the x-axis, the only length that would vary would be along these heights. So these curves, as you can see, the undeformed and the deformed length are similar, and only the varying length is this. So these are the 12th. These curves are nothing but all varying along the z-axis, and since this can be seen through the deformation map too. Now computing the deformed length of one curve using hand calculations. So the curve I've chosen is this curve. Its parametric equation for the undeformed curve is basically this, and the undeformed length is 12. The deformation map is given by this. Substituting the parameterization for this, like replacing x with 3, y with minus 2.5, and z with s, we get the parameterization of deformed curve. Tangent vector, computing the tangent vector of the deformed curve, and to compute the length we just take square root of squares of the components of the tangent vector. So in this case it is square root of this term, square root of square of this term. So basically it becomes this, and the differentiating with respect to the parameter s and varying from 0 to 12, we get a value of 1728 units. And from the MATLAB we also got this value only. I'll quickly review my MATLAB code. So here you can see the code is running pretty well, and the command window. So here we can see we receive a length of as stated in the presentation. Thank you.